Hello everyone, today I am presenting our team's latest work, which has been accepted by ICCV 2025, DISTA-Net, Dynamic Closely Spaced Infrared Small Target Unmixing. Our paper and code have been uploaded online, and you can access them via the link or QR code above. Feel free to check them out. I will introduce our work from the following aspects. The application of drones in modern warfare is now commonplace. When large numbers of drones or missiles appear at long distances in clustered, high-density formations, optical diffusion causes severe aliasing in infrared imaging. Multiple targets may be concentrated within just a few pixels, making it difficult to accurately determine their quantity and precise locations. This significantly impedes subsequent stages of detection, tracking, and identification in infrared search and track systems. This underscores the critical importance of the closely spaced infrared small target unmixing task. In simple terms, XIST unmixing is the problem of precisely identifying the quantity, location, and radiant intensity of such distant, closely spaced infrared small targets from limited pixel information. This task differs fundamentally from traditional infrared small target detection. Although both focus on infrared small targets, key distinctions exist. 1. Stage in the processing pipeline. Traditional infrared small target detection is a prerequisite for XIST unmixing. It is responsible for initially detecting the overlapping target cluster, forming the essential foundation for our task of predicting subpixel locations and radiant intensities. 2. Nature of the prediction. Unlike the traditional binary detection paradigm that simply determines target presence or absence, our research achieves multi-dimensional target characterization through subpixel localization and radiant intensity estimation. This provides a more profound solution for understanding infrared target characteristics, enabling deeper cognitive analysis. Therefore, to foster continued advancement in this field and for this specific task, we are also committed to building a comprehensive research ecosystem for closely spaced infrared small targets. This effort encompasses a complete suite of solutions from datasets and evaluation metrics to toolkit development and explores effective techniques for both unmixing and reconstruction. When a single-point light source is imaged through a lens, a diffraction pattern known as an airy disk forms at the focal point. It is characterized by a bright central disk surrounded by multiple concentric rings of alternating bright and dark fringes. This diffraction effect is commonly approximated using the point spread function. The standard deviation of the PS depends on the sensor lens focal ratio and the wavelength, and is used to quantify the degree of energy spread. Under these conditions, the response of an imaging pixel ij, to a target located at xy, and be represented by the integral of the PSF over the pixel's boundary. In multi-target imaging, the radiant energy of each target spreads across the focal plane due to optical diffusion. The radiation intensity captured by each pixel represents the cumulative response from multiple point source targets, following the principle of linear superposition. Based on this focal plane imaging model using a two-dimensional Gaussian diffusion function, the infrared image can be expressed as C equals GS plus N. Here, G is a guidance matrix, where the value in the ith row and jth column represents the response amplitude of the ith pixel to the jth target. The challenge of this problem lies in the scenario where targets are extremely close to each other, particularly when their spacing is smaller than the radius of the airy disk. This defines the physical resolution limit of the sensor for distinguishing to point sources, also known as the Rayleigh criterion. In this context, one revolution is approximately equal to 1.9 times sigma, which is specifically determined by the detection wavelength and the lens diameter. Traditional approaches typically frame this challenge as a parameter estimation problem and solve it using optimization algorithms. However, their performance depends heavily on careful hyperparameter tuning, limiting practical usability. Changes in target number or location further complicate hyperparameter selection, reducing generalization and practicality. While deep learning has revolutionized image super resolution, its use in XIST unmixing remains largely unexplored. This is due to fundamental task differences. Rather than enhancing visual clarity, XIST unmixing requires estimating the count, position, and intensity of overlapping targets, mapping images to target attributes, not to higher resolution pixels. Progress is further hindered by the absence of standardized benchmarks, dedicated metrics, and open-source tools, impeding development and fair comparison of deep learning methods in this field. In this study, the sigma value was set to 0.5 pixels. Our simulation experiments covered images containing 1 to 5 overlapping targets, each defined by 2D coordinates and radiant intensity values ranging from 220 to 250 units. The targets were concentrated within random single pixels while maintaining a minimum spacing of 0.5 to Rayleigh units. Under this configuration, a dataset named XIST-100K, comprising 100,000 samples, was generated, with 80,000 samples forming the training set and the remaining 20,000 equally divided between the validation and test sets. The first row illustrates the aliasing scenarios with 1 to 5 targets, while the following 3 rows display the unmixing results at different magnification segments. As shown in the figure, the energy of XIST diffuses in the image plane, primarily concentrated within a 3 pixel area. This leads to significant aliasing, making it extremely challenging to determine the number of targets and their precise spatial coordinates. Inspired by the mean average precision map metric commonly used in general object detection, we propose closely spaced object map to evaluate the accuracy of XIST detection. A CSO matching criterion is introduced, where a predicted point is designated as a true positive TP only if its distance to a ground truth target is below a specified threshold, and that ground truth target has not been matched with another predicted point of higher intensity. Once predictions are classified as TP or false positive FP, a binary list is constructed following the common practice in COCO evaluation, where TP predictions are marked as 1 and FP predictions as 0. By dynamically adjusting the detection confidence threshold, a series of precision and recall values can be obtained, forming the precision recall PR curve. The average precision AP is then calculated as the area under this PR curve, providing a comprehensive assessment of the model's performance across different confidence thresholds and effectively summarizing the trade-off between precision and recall. Under the premise of allowing a certain degree of quantization error, the possible positions of targets on the image plane are finite. Based on this characteristic, all potential sub-pixel positions can be exhaustively enumerated to construct a complete set of possible target positions, expressed by the following formula, where L denotes the finite number of positions. This ensures that the set of actual target positions in XIST must be a subset of omega. As long as the grid is sufficiently fine, each subpixel can contain at most one target. The position set is represented as the collection of all subpixel centers. By computing the guidance matrix G, based on the complete position set omega, an over-complete representation of the measurement model can be obtained. This measurement model is reformulated as a sparse representation, transforming the far distance XIST unmixing task into a sparse signal reconstruction problem. The iterative shrinkage thresholding algorithm, DISTA, is a classical first-order proximal method particularly well-suited for solving large-scale linear inverse problems. It addresses sparse reconstruction by alternately performing 2 update steps, denoted as 1 and 2. Detailed computational methods can be referred to in the provided link, which offers a comprehensive introduction from convex optimization to deep unfolding. However, with this approach, the weights of the transformation network and key iterative variables remain fixed after training. This makes it difficult to adaptively adjust the feature extraction strategy when facing complex and varying XIST unmixing scenarios. To address the limitations of static networks, we introduces a dynamic mechanism via two key improvements. Dynamic Transformation Module uses a dual branch design with dynamic kernels for adaptive feature adjustment, enhancing representational power. Dynamic Thresholding Module leverages dual convolutional layers to capture multi-scale features, improving robustness against sparse vector perturbations in reconstruction. The implementation follows Algorithm 1. First, gradient descent updates are. The proximal mapping then involves 3 steps. 1. Applying dynamic transformation to our using S. 2. Generating adaptive thresholds via a dynamic threshold generator and performing soft thresholding. 3. Reconstructing through inverse transformation. These steps iterate in times. DISTA-Net maps iterations to network layers, enabling end-to-end training that optimizes parameters automatically while maintaining interpretability. The dynamic transformation uses a dual branch structure. The upper branch processes R via conv-relu-conv. The lower branch uses an MLP on S to generate input-dependent convolutional kernels applied to R. A sigmoid-weighted sum combines both outputs. The dynamic threshold generator employs a multi-scale soft selection mechanism. Features from 3.3 and 5.5 receptive fields are concatenated, processed with pooling and 1.1 convolution, then fused via sigmoid attention to produce spatial varying thresholds. The inverse transformation uses conv-relu-conv to restore features. Training combines a messy loss with a consistency constraint between transformed and inverted features. Network initialization uses simple linear mapping. We conducted experiments on the XIST-100K dataset, comparing our method with traditional optimization algorithms, image super-resolution approaches, and various deep unfolding methods. The results demonstrate that our approach maintains a leading advantage, effectively balancing computational efficiency, localization accuracy, and reconstruction quality across comprehensive evaluations. We also compared the performance of different methods across various sampling grid resolutions. DISTA-Net consistently maintains a leading advantage in localization precision, outperforming all other methods under every configuration, particularly in metrics within the inherent error tolerance range. Regarding hyperparameter selection, we have also conducted extensive experiments on the relationship between model performance and the number of stages. Finally, we compared the reconstruction performance of different methods and scenarios involving 3 to 5 closely spaced targets using 3 sub-pixel division, evaluating their effectiveness in handling spatially adjacent infrared multi-target scenes. Existing methods demonstrate limited performance in reconstructing closely spaced targets, often exhibiting blurred boundaries or target merging. This performance degradation becomes more pronounced as the number of targets increases, particularly in 5-target scenarios. In contrast, DISTA-Net successfully preserves both the target count and sub-pixel positioning, even under high overlap multi-target conditions, while maintaining clear boundaries and accurate spatial distributions. The right figure also illustrates DISTA-Net's performance at higher subdivision rates of 5 and 7, where the model demonstrates significantly enhanced unmixing effectiveness under these refined grid configurations. Thank you for your attention. Should you have any questions, please feel free to contact us.